So there's an important aspect of all of this vector work of how do you compile for this? Well, thankfully, we actually have compilers that can do automatic vectorization. And one of the challenges here, if you look at this element-wise multiply, is you have a loop that's running and another loop that's running, and your compiler needs to figure out that it can merge those loops and run them at the same time. And compilers actually have gotten pretty sophisticated. If you go look at the Cray compiler now, it can basically do outer loop parallelism. It can do certain types of parallelism with loop carried dependencies and vectorize all of this. But it requires some pretty deep compiler analysis. This especially works well for things like Fortran codes where you don't have random pointers pointing different places. C code, this gets a little bit harder. So what if you don't want to execute the same code on all the different elements of your vector? Well, that could be a problem. So here we have a piece of code which loops over some big vector. This is C code. And it checks to see whether the value is greater than 0. And only if it's greater than 0 does it do this next operation. So there's been extensions to vector processors that have allowed effectively predicates or mask operations on a per element basis of the vector. So the way you would do this is you would actually load the entire vector, set a mask register where you have a 1 or a 0, which is the result of this comparison on an element by element basis, and then do the operation. And you can basically put this together with these bit-by-bit comparisons and have slightly different control flow for the different elements within a vector. And just sort of showing the implementation of this, if we looked at how to actually implement masking, one way to do it is you actually do every operation. So let's say you're doing multiply and your vector length is 64. You do all 64, but you just disable the write to the register file on the ones that have the mask bit turned off. Or you can have a much more fancy implementation which takes out the work that doesn't have to be done. But the control on this is quite a bit harder. And I would say that this is probably more common, just the simple implementation. And this is harder largely because if you have the resources anyway, so if you have multiple lanes, it might just make sense to go execute and sort of annul the operation later. Some other things that are pretty common in vectors is you want to have reductions. What I mean by reduction is if, let's say, you have this array and you want to add all the elements in the array into a variable. This is sort of a vector to scalar operation. You can't really do this on what we've discussed so far. You can't do a vector operation which will actually operate on all these values and try to do something useful with it. But what you can do is you can try to do some software tricks. So one of the software tricks is you can take a whole vector and instead call it 2 vectors, sort of cut it into half, and then overlap them and do parallel adds. And then you take the results of that, you take it someplace else in there, and you take those 2 parts and you overlap them and you do adds. So you can do lots of parallel adds and effectively build a reduction operation by building a tree of adds. So if we have our vector here, we would cut it in half and add this part with this part, and then the result would be half the size. And we cut it in half, and we add this part with that part, and the result is half the size. We cut it again, we keep doing adds. So we can use our vector arithmetic to effectively do a reduction. So we're about out of time here. Talk about scatter gather. This isn't that deep. The implementation of this can be very hard, though. A of D of I. So we want to index based off an index of the vector. This is called gather. Scatter is the other direction when you're doing the store with a doubly index of an index. And in the instruction set in your book, they actually have an instruction to do this. LVI here, what that basically does is it takes each element of vector D here, indexes into vector C, and then that is that result. Problems with this is, of course, your memory layout is not going to be all nicely laid out in memory. You're going to be sort of jumping around in memory. Let's stop here for today, and we'll talk a little bit more about vectors and GPUs next time.